Now that we've finished learning scheme, every week a mind-blowing new idea. This week's mind-blowing new idea is function as data. So this is your brain. And unless you're one of the handful of born mathematicians, in your brain there's this big brick wall between the notion of stuff and the notion of actions. So that's why in our languages, every human language has nouns and verbs as different categories. We talk about knowing that such and such versus know how to do such and such. And in computer programming, there's this big distinction between data and procedures. There's two different kinds of things. Data is stuff like numbers or character strings or whatever. And procedures, you know what procedures are. So our job throughout the course of the semester is to try to break down this wall in your heads. But it really is going to be hard. It's something you're going to have to stretch your minds around. This wall, for example, to take a non-computing example, this is the reason freshman calculus is notoriously difficult, even for some people who did well in math in high school. There's this sort of big, hitting the wall about calculus. And calculus students think it's because of details about, integration by parts or something. But it's not. It's because the integral itself as a thing is a function of functions. So the integral doesn't take some number and give you out a different number. It takes a function like f of x equals 3x squared and gives you a different function like f prime of x equals 6x, right? And it's wrapping your mind around this idea that you can have a function whose argument is another function that makes calculus hard. And it's also what makes this week's topic hard, functions as data in the computer programming context. So we're going to sort of inch up on it by starting with a simpler idea, which is generalizing patterns. And remember, as we do this, I'm going to show you a very, very simple example of it. So keep in the back of your mind, the reason is we're building up to procedures as data. So up on the top half of the screen, after we define pi, there are 4 procedures that compute the areas of various geometric figures. So if we have a square of side r, its area is r squared. If we have a circle of radius r, its area is pi r squared. If we have a sphere of radius r, its surface area is 4 pi r squared. If we have a regular hexagon of radius or side, because they're the same thing in a hexagon, r, its area is 3 root 3 over 2 r squared. Okay, 1.5 root 3 r squared. So we can use these procedures. Whoops, stop doing that. So I can say, circle area 5, and I get 25 pi, which is a little more than 25 times 3. Right? But I don't like the idea of having a separate procedure for each of those. I would like, and I notice that there's a pattern in here. What's the pattern of those 4 area procedures? Yeah, it's all some number times r squared, right? Because area is 2-dimensional, r is 1 dimension, so, okay? So, here's how I'm going to do that. my original procedures took one argument, which was the linear dimension of the thing. My new procedure takes two arguments. I've added an argument that's going to embody what's different from one of these procedures to another. So what's the same is, for every shape, it's some constant times r squared. And what's different from one figure to another is what the constant is. So for a square, the constant is 1. It's just r squared. For a circle, it's pi r squared. For a sphere, it's 4 pi r squared, and so on. Okay, so now I can say area, circle, 5, and get the same answer. And the same would work for any of these other figures. Okay, so I want to make sure you get how this is a generalization, that the original area procedures, each one took one argument for the linear dimension. The generalized procedure still has that argument for the linear dimension, but now it has another argument that says what's different from one pattern to another. Okay? Any questions about this so far? Great. Okay. What makes this a really simple example is that I was able to capture the differences in just a number, right? The constant factor. So I can define circle to just be pi. But sometimes the pattern is a little more complicated. So here I have, this is an example taken from the book. I have a procedure that computes the sum of the squares of the numbers from a to b. So if I say sum square 3 to 5, I should get 9 plus 16 plus 25, which is 50. Okay? So is it clear how that works? It's a squared plus a plus 1 squared plus a plus 2 squared, dot, 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 up to b squared. So how does this procedure work? It says, well, if there's going to be a recursion, so we have to have a base case. The base case is if a is greater than b, then we're not adding any terms at all. So therefore, the answer is 0. If a is less than or equal to b, then there's at least one term to add, namely a. So we're going to add a squared, which is this, to a recursive call going from a plus 1 to b. Okay? Similarly, we have some cube. If I say some cube from 3 to 5, I get some number that's much too hard for me to compute in my head, namely 216. And that's 3 cubed plus 4 cubed plus 5 cubed. Okay? Now, what I want you to see about those two procedures is that they're almost the same. Namely, they both say if a is greater than b, return 0. Otherwise, add some function of a to a recursive call for a plus 1 to b. So the only thing that's different here is that in this case, it's the square of a, and in this case, it's the cube of a. Okay? So I'd like to generalize this pattern. But the way I have to represent what's different between these two versions is no longer capturable as just a number. Okay, these are two different functions. So I'm still going to have an extra argument for what's different. But this time, instead of a number, the argument is going to have to be a function. Okay? So I'm going to say, define sum, just plain old sum, of some function I'm putting it in capital letters just so you can see what's different here. And A and B. So one new argument function. And then it's going to say if, oops, greater than AB, don't ask me why that is like that, then return 0. Otherwise, add. Now, I have to take that function and apply it to A, right? Well, that's how we do that. To call a function, you put it in parentheses along with its arguments. So function of A, and then sum of function A plus 1 and B. Close, 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 close. Okay? Yes? Shouldn't the A be a lowercase a? This is a sensible programming language. It doesn't pay attention to case of letters. Sadly, this is no longer true if you look at the latest scheme standard. It got hijacked by Java fans. And so they're making identifiers case sensitive. But if you have 3 things in your program called foo, and one of them is lowercase foo, and one of them is capital F, lowercase oo, and the third one is capital F, capital O, you're asking for trouble. So sensible programming languages, it doesn't matter. Okay? It's a bad habit. Get out of it. That they taught you in high school. Sorry, I'm not making fun of you. I'm making fun of your high school teacher. Okay, and it isn't even your high school teacher's fault, really. I'm making fun of the College Board, who has the AP curriculum in Java, instead of Scheme. Okay, other questions? Okay, so now I'd like to use this. So I say sum x squared from 3 to 5. Is this going to work? No, it's not going to work. Why not? It says unbound variable x. When I said times xx here, remember Scheme uses applicative order. That means before it calls sum, it's going to try to multiply x by x. But I don't have an x. It wouldn't help if I said a, because there isn't one of those either. Okay? So we have to find a way to give it a function as an argument rather than a number. So right now I'm going to do that this way. I'm going to define a function, square. And now I'm going to say sum square from 3 to 5. And I get the answer I wanted. Okay? Please note that there is no open parenthesis before this word square. You all know, right, that the singular of parentheses is not parenthesis. It's parenthesis, S-I-S. So there's no open parenthesis before the word square. That's because I'm not invoking the function square. I'm just taking square as a thing and passing it as an argument to sum. So you see how we're breaking down this wall? Because square started out life over here as an action. And now I'm using it as a thing, as data for this other procedure, sum. Okay? Yes? Won't Scheme try to evaluate square? Yes, it will. It will evaluate square. The value of square is this ugly thing, which is how STK prints out procedures. So it's perfectly OK to evaluate square. But I'm evaluating it is not the same thing as invoking it. Okay? What I'm evaluating is the word square. The value of that word is a function, a procedure. Okay? If I say parenthesis square such and such, then I'm invoking that procedure. I'm actually running it with arguments. Okay? Good question. Other questions? Okay, moving on. The version in the book, by the way, just backing up to the definition of sum here, they add another complexity, which is to allow you to use a function of your choice in going from one value of the variable to the next. So if you want to add up all the squares of odd numbers between 1 and 10, you could say some square function 1, and then the function of x that's x plus 2. So add 2 function, and then 10. And it would do 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared. And then we would try to do 11, but that's bigger than 10, so that would be the base case. So that's just, an added level of generality that they added. For lecture purposes, I try to make things as simple as possible. So this was the simplest way to get a function in as an argument. Okay. Once we have this idea of function as argument, we can use it to generalize many, many, many interesting patterns. So So here I have a function evens up at the top of the screen. What it does, it takes a sentence of numbers as an argument, and it returns the subset of that sentence that's even numbers. So I say evens. Okay, wait. Whoa. Okay, let's try this again. Evens, quote, 3, 5, 1, 4, 9, 8, 6, 7. And I get 4, 8, 6, which are the even numbers out of that sentence. So does everybody see what the function does? What value it computes? Good. Okay. Some people aren't thumbing. If you don't thumb, then I'm assuming up. If that's not what you want, give me a thumbs down. Okay. How does evens work? Well, it's a recursive procedure. So first we have a base case, which is if nums is empty, then we return the empty sentence. Why do we do that? Well, the range of evens. Oh, yeah. I think I forgot to say this last week. The two most important words in the English language are domain and range. The domain of a function is what kinds of things does it take as arguments. The range of a function is what kinds of things does it return as its result. So the domain and range of evens are both sentences. So in the case of an empty sentence, I still have to return a sentence, and the one that I'll return is the empty sentence. Okay? As opposed to some other procedure that might have, say, numbers as its range, and then the base case I might return 0 or 1 or whatever makes sense. Okay, so if we get down here, then the sentence isn't empty, so therefore it has a first word, which in this case is going to be a number, and this complicated formula is just asking, is that number even? So I take the number, I take the remainder on dividing that number by 2, and ask the question, is this equal to 0? As it turns out, I could have just said even question mark first of nums. But I like doing it this way because it's a good example of composition of functions to remind you that the way scheme evaluates an expression like this is not left to right, it's not right to left, it's inside out. So the very first thing that's going to happen is we figure out first of nums, which is, in this example, 3. And then, surrounding that, we take the remainder on dividing 3 by 2, which is 1. And then I say, is that remainder equal to 0? And the result of that is false. Okay, so for 3, we're not going to do this thing which is the action. But for an even number, like when we get to 4, we are going to do this. So what is it we want to do if first of nums is even? Well, we want our result to include first of nums because it's even. What else should it include? Well, it should include all the even numbers of but first of nums. So I had a few people show up in office hours this morning who had the same problem. They wanted to say first of nums, new line, evens of but first of nums, do those two things. That's it. You can't do that. A function has to return one value. So if you're accustomed to thinking about programming in terms of first do this, then do this, then do this, try not to think that way and think, what is the one value that I want to return? And the answer is, I want to combine first of nums and the recursive call into a sentence. Sentence is the primitive sentence constructor. Takes any number of arguments. They can be words or sentences mixed together, and it sort of strings them out into a sentence. So our result sentence is going to include first of nums, and it's also going to include any even numbers that might come after first of nums in the sentence. Okay? And then the third con clause is otherwise, namely we have an odd number. If we have an odd number, then I don't want first of nums to be part of the result. Right? Because we only want even numbers. So I'm just going to call evens on but first of nums, and whatever that returns, that's what I'm going to return too, throwing away first of nums. Okay? Questions about how that works? Yes? Sentences as opposed to? Oh, we haven't invented lists yet. That's chapter 2. Sorry? Sentences. Basically, she's reading ahead. Or she took CS3 or something. Lists are a more complicated data structure. Sentences, okay, so the structure of the book, the first part of the book, there's chapter 1, which is all about procedural abstraction. It's about controlling the flow of control of a program. So how do you say, you know, here's what I want you to do, and what mechanisms do we have to help you do that? And that's what chapter 1 is about. Chapter 2 is about data. And we get into data structures and how to build them up. And they did it that way because there's some complexities about both of them, and they only wanted to throw one kind of complexity at you at a time. Now, in order to make that work, the book uses, in chapter 1, entirely mathematical examples. That's because the book comes from MIT, where, you know, everybody speaks mathematics, even the business majors. There aren't any English majors. And for our purposes in Berkeley, I wanted to provide more interesting data from the beginning, but without running into the complexities of lists. And sentences are kind of an idiot-proof data type. You can't build the wrong thing by accident with them very easily. So once you get flow of control under control, then we'll go on and talk more about data, okay? And we'll revisit this question of sentences and what they are and why. Okay, other questions? Okay, moving on. E-words. Get life. So eWords takes a sentence and it returns the subset of that sentence consisting of words that include the letter E. So in got to get you into my life, got and to and you and into and my don't have the letter E, but get and life do. Okay? Fortunately, the word A doesn't have an E in it, so it doesn't say get a life. All right, how does eWords work? Well, it says, if my argument sentence is empty, return the empty sentence. Then it says, okay, the sentence is not empty, so it has a first word. Does that first word contain the letter E? So remember question mark of a one-letter word and a word will return true if that letter is in the word and false if that letter is not in the word. You can also do member question mark of a word and a sentence, and it does a similar thing. Returns true if the word is in that sentence, false otherwise. So, is the letter E in that first word? If so, then I want to include the first word in my result, and I also want to include a recursive call for the but first. If not, if there isn't an E in that word, then I just want to return a recursive call for the but first. Yeah? Is SE the same thing as append? He's another list guy. SE is the constructor for sentences. It is subtly different from append for lists because it accepts words as arguments. But a general rule for you guys who learned about lists last semester, try not, and actually this is a good piece of advice for everybody who learned anything about programming before this semester. As we're doing stuff, try not to do it by mentally converting what you're learning to what you already know. Okay? And it's for the same reason that teachers of foreign languages tell you this. You know, when I was learning French in high school, they told me correctly, try not to translate what you're reading into English. Try to think in French. Right? Because you never get any good at it until you can think in French. And the same is true here. If you convert into what you did last semester or convert into what you did in high school, you're going to miss the point, I think. Okay? So, you know, try and stay on the same page with the rest of us. All right. Other questions? Yeah. Okay. Oops. Okay, here we go. Okay, pronouns takes a sentence as an argument, and it returns the words of that sentence that are pronouns, which is to say, ones that are in this list, which, yes, is not really exhaustive. It leaves out all the possessives and so on. How does it work? Well, if the sentence is empty, then return the empty sentence. Otherwise, the sentence has a first word. So ask, is that first word one of these words? If so, return a sentence that contains first of sent and also contains the result of a recursive call for the but first. If not, if it's not a pronoun, then just return pronouns of but first of sent. Okay? So these three procedures have a very similar pattern, right? Yes? Why use a member instead of equal? Because first of sent is going to be something like I or only. It's not going to, let's say it's I. Is I equal to this sentence? No. I isn't a sentence at all. And it certainly isn't, this sentence. I doesn't have a me or you or he or she or it in it. So it's not equal to that, but it is a member of that. They're two different relations. Does that answer the question? Good. Okay. Oops. All right. So, I want to generalize this pattern. So I'm going to take a predicate function as an argument, because that's what's different. It's what test do we make of first of sent. And it takes a sentences argument just like the other ones. And I'm going to say cond empty sent, return the empty sentence. That's the same in all of them. Now what? Pred of first of sent. If pred of first of sent is true, then sentence first of sent and a recursive call with the extra argument pred, the same, and but first of sent. Else, just the recursive call. Okay? So compare this with the ones on the top half of the screen and see if you agree that it captures the pattern. Right? Namely, the only thing that's different is this part, where we make some particular test about first of sent. Everything else is the same. So what we need is to capture that test. And again, a test is an action. It's a thing to do. So it has to be a procedure rather than a number or a character string or a sentence or any of those things. Okay? So now I can say keep even question mark ta-da. Okay. The other ones, again, I would have to define e-word question mark of word to be member question mark quote e word. So make a function just for words. And now I should be able to say keep e-word question mark and get the answer I want. Right. Okay. Questions? Yeah. Is there any advantage to cond versus a stack of nested ifs? Just that your code is prettier. If you keep nesting ifs, everything marches further and further toward the right margin, and your line space in the window gets smaller and smaller. That's all. And also, as soon as you see the word cond, you're thinking, okay, this is a multi-way choice. So it helps the reader understand the structure, I think, a little bit. But Scheme doesn't care. Okay. Yeah. Are there any exceptions to the thing where we have to define a function and then stick a function in the function? I did not pay him to ask that question. Let's do something new. What's this? Well, glad you asked that question. Back in high school, or middle school, or whenever it was, your algebra teacher was very sloppy about notation and said things like, the function ax plus b. Right? Ax plus b isn't a function. Ax plus b is a number. We don't know what number it is until we have values for a and x and b. But that expression represents a number. Real mathematicians would say the function x maps to, that's pronounced maps to, ax plus b. There are a lot of advantages to this notation, one of which is that unlike this one, it makes clear what it's supposed to be a function of. Okay? In high school, they use more or less explicitly this convention that letters near the beginning of the alphabet are constants and letters near the end of the alphabet are variables. But suppose we had an expression like xy plus z. Well, there are a lot of functions this could be. Maybe it's the function y maps to xy plus z, and somebody's going to tell us the values for x and z separately. Maybe it's the function x comma y comma z maps to xy plus z, where it's a function of 3 arguments. Maybe it's y comma x comma z maps to xy plus z. Well, that's the same function. X, z, y. There. Now it's a different function. Right? So saying what your parameters are of your function, the formal parameters, helps you understand what function you're talking about. Sadly, this character does not appear on your computer keyboard. If you're printing it in a paper, you can say, if you're using tech, you can say \maps to, and it'll print that. But that's not how we do it in our programming languages. The way we do it is based on the work of a guy named Alonzo Church, who is, I guess, a mathematician. Did he die yet? Church? I don't know. He was alive a few years ago, so he may still be. he invented a formalism for trying to talk about mathematical ideas based on the notion of functions. And there's a long story about this, which I'm not going to tell you right now, probably, unless we have time at the end. But in his representation of functions, he used the Greek letter lambda, which looks like that. It's Greek for L, basically, to represent the thing that makes a function. So instead of saying x maps to ax plus b, he would say lambda x dot ax plus b. That was his notation, except that he wouldn't say this because there was nothing but functions in his language. And so it's a little messier, but this is the lambda part. So a function of x that has this body. And we don't have a lambda on our keyboards either. I got my introduction to computing at the MIT Artificial Intelligence Lab and then the Stanford Artificial Intelligence Lab. And their keyboards do have lambdas because they do all their, not all, but a lot of their programming or did in Lisp, which is a language developed for artificial intelligence. So they use lambda a lot, but we have to spell it out. I will write it on the board using lambda, the letter. But when you're typing it into the computer, you have to say lambda. So the notation is lambda, and then a sentence, basically, of formal parameters, and then an expression, which is the body of the function. So this is the function WD maps to, remember question mark quote E, WD. Yes? I'm sorry, say it again? Tell me when. Okay. Oh, the keep function. Yeah. Okay. So did you understand, for example, how eWords works? Yes. Okay. So keep works the same way. Compare it. Cond. If the sentence is empty, return the empty sentence. Okay? Now, if the first word of the sentence contains the letter E, that's what this says. In keep, I'm generalizing that, the same as I generalized the area function back at the beginning. That was the point of that thing about the different kinds of areas, is the idea of generalizing a pattern. This is the part that I'm generalizing. And you capture a generalization by having an argument for what's different between the instances of this generalization. So what's different between eWords and pronouns? It's this part, right? Versus this part. That's what's different. Those things are expressions whose value is true or false. Now maybe I have to explain the word pred. Pred is short for predicate. A predicate is a function whose range is true and false. True and false are called Booleans. So a predicate is a function whose range is Booleans. So this expression produces a true or a false. So a function to compute this expression will be a predicate. And what I do in the generalized version is I take whatever predicate I'm given and call it with first of sent as the argument. Okay? And all the rest of this is exactly the same as before, except that the recursive call has this extra argument pred in it. Does that answer your question? Okay. Any more? Yeah. So is there a difference between using a lambda and defining a function with define? There so much isn't a difference. I didn't pay him either. There so much isn't a difference that, in fact, when you say define square x times xx, all this is an abbreviation for define square lambda x times xx. Okay? This is the same kind of define as if I said, define foo plus 2, 3. Right? So we evaluate the plus 2, 3. The value of foo is 5. Right? Now, what's the value of a lambda expression? If I say lambda x times xx, what do I get? What do I get? I get that. That's a procedure. Lambda returns a procedure. Lambda makes a procedure. Lambda is how you make a procedure. Okay? So the way you learned last week, this way to make a procedure, you now know actually has hidden inside it a lambda. Because lambda is the only way to make a procedure. Okay? So we evaluate this lambda expression, but that does not entail evaluating its body. Right? When we create the square procedure, we don't evaluate times xx. That doesn't happen until we call this function. Right? So I could say, open paren, lambda x times xx of 6. I get 36. Okay? So lambda makes a procedure, and you can call that procedure just like any other procedure. Usually, you don't type stuff like this. This is a very roundabout way of saying 6 times 6. What you use lambdas for, is to use them as an argument to a procedure like keep. A procedure like keep is called a higher order procedure. Higher order meaning that either it takes a procedure as an argument or it returns a procedure as its value. That's what higher order means. Higher order, now, procedures represent functions. Remember we had that discussion last week. A higher order procedure represents a higher order function. A higher order function is one that takes functions as arguments and or returns a function, like, for example, derivative and integral. In calculus are higher order functions. Keep is a higher order function. It doesn't return a function, but it takes a function as one of its two arguments. Okay? And it does that in order to generalize a pattern. Generalizing patterns is how we keep our programs from getting really long. Remember I said last week, programming is easy as long as you can see the whole program at once? When the program gets too big to look at it all at once, it gets hard. So the way we make programming possible is to try to make our programs smaller. And we do that by cramming more into the same amount of space. And one way to do that is generalizing patterns so that you don't write almost the same code over and over again. Instead, you write it once, generalized, like keep. Okay, see you Wednesday.